Hello everyone, I'm Yizhe Shi. Due to visa issues, none of the authors are able to attend the conference. Therefore, I will be presenting this paper, Blackbox Fuzzing of Distributed Systems, on their behalf. Distributed systems power many modern infrastructures, but bugs in these systems can result in significant economic losses. There are different applications. Distributed databases like ClickHouse and RacingDB provide fundamental support for analytical and computational tasks. Distributed coordination systems form the backbone of modern data center infrastructures. So it's important to ensure the safety and robustness of these systems. Though different distributed systems have different goals, they share many common features. First, they usually accept various kinds of input events, like the first figure shows, and the events can divide into two types. One is regular events like client inputs, the other is fault events like network failures. Second, network messages capture important state changes of a running distributed system. As the figure shows, in Raft, all state changes are either triggered by receiving certain network messages or timeout, which in turn makes nodes send out network messages. In both cases, the important state changes can be captured by network messages among nodes. Finally, distributed systems heavily use the timeout mechanism, so we need to consider timing dependencies between events to generate more effective test cases. The complexity of distributed systems lies in these common features. However, current tools are not fully designed based on these features. Tools like JSPN, CrashFuzz, and Mallory have limitations such as limited feedback metrics and lack of systematic input generation. Therefore, this paper proposed DistFuzz. DistFuzz is designed to address these gaps. DistFuzz builds on efforts with extended input space and effective feedback mechanisms. These papers key contributions include an extended mutation space with regular events and timing intervals, and an effective symmetry pruning feedback for pruning redundant sequences to guide the fuzzing process. Our prototype tool produces impactful results, including the discovery of 52 bugs across 10 systems. 4 of the bugs were assigned CVEs. Compared with other tools, we extend the mutation space with frequent and guided mutations on regular events and mutated timing intervals. Regular events such as client requests form the core of the input space. These events include operations like get or put commands to get and put values in the system. Timing intervals are relative intervals between events, testing the timing sensitivity of systems, which is critical for scenarios like leader election. This figure shows a test case with regular events and specific timing intervals. This test case triggers a bug in RacingDB that makes newly created databases unusable. This bug needs a regular event sequence with specific timing intervals. Indicating mutations on these two types of events are important. Besides, DistFuzz systematically commutates combinations of regular events, faults, and timing intervals. To effectively represent the test case, DistFuzz encodes regular and fault events in input space as a three-tuple, including timing interval, event type, and parameters to universally represent different kinds of events. As the figure shows, a test case file is translated to input sequences. The specific meaning of the parameter depends on the type of the events. For example, the node kill event needs a parameter to specify the target node ID. More details can be found in this paper. Since we have larger input space, we need to design effective fuzzing feedback to guide the fuzzing process. As we discussed previously, network messages are sufficient because they can capture important state changes. Therefore, if there is no need to have user annotations. However, network messages are redundant, so pruning is required. A popular pruning method is symmetry-based pruning. We found that symmetry-based pruning is ad hoc and yield-suited. First, Similarity-based feedback pruning misses interesting states in distributed systems. Let's see this figure. This figure shows a motivating example with Raft. Current leader N1 sends an open interest message to follower N2 concurrently due to a network partition. N3 starts the election and sends a request vote message and then a vote granted message to N2. The change of the order of this message leads to different states. Since the difference is not significant in a long sequence, similarity-based pruning considers the two sequences similar, and thus many only pull one of these different states. Second, similarity-based pruning might also lead to employing redundant states. Let's see this figure. The figure illustrates the election process of the consensus algorithm. To start an election, node N1 sends a message to node N2 and N3. As the subfigure A and B show, no matter which message arrives N2 or N3, these two states are the same. Similarly, N1 or N2 starts the election process are also same, as the figure shows. Motivated by the example, the insight behind our pruning technique is that the symmetry in the system state is reflected by the symmetry in the network messages. We leverage two kinds of symmetry in network messages. The first is order symmetry. As shown in the figure, the difference in the order in which N2 or N3 receives the message does not lead to new states. To prune order symmetry, as shown in the middle part of the figure, this DistFuzz replaces the global sequence number with a local sequence number plus node ID. Thus, for the two different nodes, the order they send or receive messages does not result in different encodings. A second is room symmetry, where, as shown in the figure, where node N1 or N2 starts the election does not lead to new states. To prune row symmetry, as shown in the figure, DistFuzz removes all node IDs in this encoding. As a result, the encoding stays the same regardless of which node starts the election. Based on these techniques, we built our prototype for DistFuzz. To use it, users first provide a configuration, including how to initialize the system and the specific events. Then, generator will generate event sequences, and event handler will execute the event sequences. After the execution, runtime monitor will collect network message sequences and send the runtime info to bug checkers. Finally, bug checkers will produce bug reports to users. For the event implementation, DistFuzz supports 20 events in total, including 11 regular events and 9 fault events. Regular events like system initialization, getting and putting values to the system usually need user input. Fault events include network message failure, network delaying node restart, and more. These events are universal because they are based on system call interception mechanism like streets. DistFuzz deploys 5 checkers, including memory checkers for low-level languages, learnability evaluation checker for consistency, node crash checker that detects unintended crash, availability checker that checks whether the system is still functional after testing, and log checker to detect fatal logs. DistFuzz also supports integrating checkpoint and bug reproduction into the workflow. It utilizes the CRIO tool to check a point and restore the system before testing to accelerate the boot process. After a bug is detected, users can use the record and replay debugger and the event sequence to reproduce the bug offline. As shown in the table, we evaluated DistFuzz with 10 open source and popular distributed systems, written in 3 languages, C, C++, Go, and Java. 2 of them are to industry Raft implementations, and the other 8 are production-level distributed systems. DistFuzz is based on the common characteristics of distributed systems, and we believe DistFuzz applies to other distributed systems as well. DistFuzz in total finds 52 value bugs in the 10 distributed systems, we have reported these bugs to the related developers, and 28 of them have been confirmed. Among the 28 confirmed bugs, 13 have been fixed by related developers, and 4 new CVEs have been assigned. Compared to other tools, DistFuzz can find more bugs in all 10 tested systems. That's all. Thanks for listening. The tool is open source in GitHub. You can scan the QR code to get the code. If you have any questions, you can contact the authors. Thank you.
Yeah, so thank you very much. Because the authors are not here, so we are not going to have a Q&A session for this paper. Thank you very much.